All right, now that we've learned a little bit about random variables and what they are, we're going to learn about how to transform and combine random variables. So just keep in mind real quick, what is a random variable? Remember, random variable is like a capital X. It is a chance process. It's an event where we don't know the outcome, but we do know that it could be of several things. We talked about two different types of random variables, discrete and continuous. Discrete, listable; continuous, unlistable. So let's first talk about the idea before we actually get into some examples here. That's what the majority of this video is going to be. Let's understand the fact that there's a big difference between transforming and combining. So I'm going to draw a line down the center here because there is a difference. When we are talking about transforming a random variable, we're talking about one random variable at a time. Just one random variable, one occurrence, one event. And we're talking about just transforming it, right? So when we transform a random variable, we could maybe add or we could subtract a constant. Okay, so we could add or we could subtract a constant like the letter b. So just add or subtract some random number. Now remember that when we add and subtract, this is actually just kind of a repeat of stuff we've already learned. Adding and subtracting only affects measures of center, only changes center. Okay, now when we're talking about random variables, we're talking about the mean. So only the mean gets affected by addition or subtraction. Measures of spread, like standard deviation, do not get affected by addition or subtraction. So keep that in mind when we're talking about adding or subtracting to a random variable. The other thing that we could do is we could multiply or divide. Now, when we multiply or divide, typically what we're doing is converting, like converting a number of something to dollars, or converting between units, or something like that. So when you're converting, when you're multiplying, you are just transforming your random variable. So here, let's talk about multiplying, or we could use the division bar for divide, by a constant, okay? And when we multiply or divide, make sure that you understand that multiplication and division changes center and spread. So when we multiply or divide, we need to change both. The mean gets affected and the standard deviation gets affected. So when we learned about random variables in the previous video, and we learned about how to find the expected value, or the mean, or the average, and also how to find the standard deviation, or the spread, we learned that multiplication of a constant affects both of these, whereas addition only affects the measure of center, the mean. Okay. Now, when we're talking about combining, random variables, we're talking about two or more random variables. They could be different random variables, okay, or they could be the same random variable repeated. So this is where we get the idea of, like, maybe we do the chance event once, and then we do the chance event another time, and then we do the chance event a third time, and maybe we do the chance event a fourth time. Now, you have to understand that this is not equal to 4x. Now, algebraically, yes, 4x is x plus x plus x plus x. But statistically, when you're working with random variables, when you do a random event 4 times, that is different than just multiplying it by 4. See, multiplying it by 4 is more of a transformation of one random variable. It's one random variable. 4 times. Here we're talking about doing a repeated random event once, twice, 3, 4 times. A little bit different. And this will come out more when we look at the examples, and I think you'll understand this a little bit better. A couple rules when combining random variables. Standard deviations never combine. Standard deviation never adds. Now, don't confuse that with the rule over here, okay? Understand that standard deviation never gets put together. You never add standard deviation. You must add variance. So, standard deviation doesn't build up, variance builds up. And again, this will be makes a lot more sense once we start looking at some examples. But to understand this idea, I want you to understand that there is a very simple connection between standard deviation and variance. Standard deviation squared is variance. So my point is, you cannot add standard deviations together when you have different random variables. You have to add their variance. That's very easy to do. All you got to do is do standard deviation squared. Likewise, the square root of variance is standard deviation. So that rule will make a lot more sense when we come to some examples, okay? So the first example I want to look at here is with a discrete random variable. All right, this is the random variable of the number of t-shirts that you could sell. Let's just I make t-shirts and I sell them on any given day. So this is in any given day. I could sell a 0, 1, 2, 3, 4, 5, or 6 random variables. 0, 1, 2, 3, 4, 5, or 6 t-shirts, and the probabilities of what's the probability I sell 0, 1, 2, 3, 4, 5 are below it. Now, I want you to learn that we did teach you this value, this formula, to find the average or the expected outcome for this random variable. We taught it to you that it's the sum of each individual outcome times its probability. So we multiply each outcome, each possible outcome times its probability, and then we add them all up. We also taught you that the standard deviation formula, the standard deviation of the random variable, is the sum of the individual outcome minus the mean squared times that individual's probability. And then you have to square root all of that. Now, what I want to show you real quick, and this is going to be really, really cool, is that there's a shortcut. There's a way for you to not have to use these formulas, and I'm going to show it with you on the calculator. Okay? The formula for the mean is not very hard to do by hand. The formula for standard deviation is. So I want to show you a really cool shortcut. Go to Stat, and go to Edit, and in List 1, you're going to put all of your outcomes, 0, 1, 2, 3, 4, 5, 6, right down here. And in List 2, you're going to put the appropriate probabilities. Just make sure they match up. 5% with 0, 8% with 1, 10%, 2, 25%, 3, 33%, 4, 13%, 5, and 6%, 6. And again, I'm showing you that those are all those probabilities that were given. Then what you're going to do is you're going to go to Stat. Once you get those typed in, Stat, one variable stats, because we still only have one variable, how many t-shirts I'm going to sell. But I need to tell it to look at List 1. That's where those options are. But I need to also tell it to incorporate the probability. So I'm going to tell it List 1, comma List 2. And this way it's going to tell me the average number of t-shirts I'd expect to sell given the probabilities. That's why you need that comma with the probabilities there. So I get an expected value here. An expected value of 3.36 t-shirts, and I get a standard deviation, which is right here, sigma 1.4596. So I get a standard deviation of 1.4596. And that is pretty cool. That's going to save you a lot of time on a test or on a quiz, so you don't have to do all that work by hand. So pretty cool that it could do all that for us. So this means that typically on any given day, I expect to sell 3.36 t-shirts, right? The units on all this is t-shirts, with a standard deviation, because I understand it might vary from day to day, standard deviation of 1.4596. Now, here comes the transformation. Let's just say that I sell these t-shirts, sell for $15 a piece. How much money do I expect to make? Well, this is multiplication, right? $15 for every t-shirt. So the average amount of money that I expect to make would simply be 3.36 t-shirts times $15 for each one. Gives me a grand total of $50.40. Very, very simple. But multiplication also affects standard deviation. So the standard deviation would get affected, and it would vary by 1.4596 times $15. And that would be $21.89. So multiplication does affect mean and standard deviation. Okay. Now let's just talk about another way I could transform this data. Let's just say that I said, you know what? I forgot that sales are doing better. I forgot that I could actually sell one more t-shirt than I originally thought. So this was supposed to be a 1, this was supposed to be a 2, this was supposed to be a 3, 4, 5, 6, and now 7. Okay? So that means I'm adding one t-shirt. So that means the mean would become 3.36 plus 1. So I would now expect to sell 4.36 t-shirts. But addition of a constant, like 1, does not affect spread. So I would still expect to have a standard deviation of 1.4596 t-shirts. That would not change because of addition. The addition of a constant, like 1, does not affect spread, but it does affect the mean. So that's a quick example. All right. Here's a second problem to take a look at, another discrete random variable, and it's the number of sweatpants that I expect to sell on any given day. So I expect to sell 0, 1, 2, 3, or 4 sweatpants, and the attached probabilities are there. Now what I want you to do is I want you right now to pause this video in a second, and I want you to use your calculator and see if you could find the expected number of t-shirts and the standard deviation for the number of, sweatpants. See if you could use your calculator real quick to practice this. Remember, you're going to use list 1 is where you're going to put in the options for the number of sweatpants. List 2 would be the probabilities, and you're going to run variable stats, list 1, comma, list 2. So go ahead, pause, try it, and come back. Okay, hopefully by now you've come back and you have found that I expect to sell 1.65 sweatpants. I'll use a SP for sweatpants. And standard deviation should be 0.9206 sweatpants. Now, if you're having any issues at all, make sure your stats wizard is turned off on your calculator if you have that option, and it should be pretty simple. Okay, so now let's just say that I want to combine two random variables, right? So now we're going to talk about combining. I want to know how many total t-shirts and sweatpants. So I want to find the expected total of how many t-shirts and sweatpants I expect to sell. Well, I expect to sell 3.36 t-shirts plus 1.65 sweatpants. So that would be a grand total of, using your calculator, 3.36 plus 1.65 would be 5.01 articles of clothing. So I expect to sell 5.01 articles of clothing. 1.65 sweatpants, 3.36 t-shirts. That's very, very simple. Very, very easy. Now here comes the tricky part, the standard deviation for the total. You do not just add the 1.4596 for the t-shirts and the 0.9206 for the sweatpants, because you're not allowed to add standard deviation. You have to add the variance. So the variance for the t-shirts would be 1.4596 squared. That's the variance for the t-shirts. And I'm going to add to that 0.9206 squared. That's the variance for the sweatpants. I am allowed to add variance. I'm not allowed to add standard deviation. So I have my combined variance, and then now, you can just do that on your calculator if you want, but now I'm going to just square root that outcome. I'm going to square root all of that to get it back to a standard deviation, because remember, variance, the square root of variance is standard deviation. So now that I have my total variance, I could square root to get a total standard deviation. So I'm going to do the square root of 1.4596 squared plus 0.9206 squared, and I get 1.7257. So 1.7257 would be my standard deviation for the total articles of clothing that I sell. So that's a really important rule, is that you never add standard deviation, you add the variance first. Okay? All right, so let's go ahead and do another discrete problem here to really kind of hammer this point home, and hopefully this will be really, really easy here. Okay, so Sally's a dog groomer, and each day she expects to groom an average of 8 dogs with a standard deviation of 1.2. So the benefit is I'm telling you the average, and let me see here. I'm telling you we expect the average to be 8 dogs that she's going to groom, and the standard deviation is 1.2. You do not have to use a calculator. You don't have to use a formula. I'm giving you these two things. Makes the problem a lot smoother. Okay, how many dogs does she expect to groom over a 5-day work week, and with what standard deviation? Okay, so this is going to be a combining, because we know what happens for 1 day. 1 day is what we were given. Now we're talking about 5 days. So we're going to have to talk about the fact that, what do we expect for the first day? What do we expect for the second day? What do we expect for the third day? What do we expect for the fourth day? And what do we expect for the fifth day? Well, the good news is we expect 8 dogs that first day, 8 dogs the second day, 8 dogs the third day, 8 dogs the fourth day, 8 dogs for the fifth day. So over the course of a 40-day work week, we expect to groom 5-day work week, we expect to groom 40 dogs. Now, I know that you could just do 8 times 5 to figure that out. And I'm not saying to not do that, but I need you to understand the fact that it's not that we're doing this it's not that it's not that the answer is 8 times 5, because it is. I know it's 40, but it's that you need to think about it as 5 separate random variables. Day 1, day 2, day 3, day 4, day 5. Each day we expect 8 dogs, hence the 40 dogs over the 5 days. Now, what about the standard deviation? Well, once again, we're not allowed to add standard deviation. We're not allowed to just do 1.2 plus 1.2 plus 1.2 plus 1.2 plus 1.2. We have to add the variance. So, to get my standard deviation, I'm going to do 1.2 squared. That's the variance for the first day, plus 1.2 squared, variance for the second day, plus 1.2 squared, variance for the third day. That's a plus sign. 1.2 squared, variance for the fourth day, and I'm running out of room over there, so I'm going to come over here. 1.2 squared, variance for the fifth day. And then I'm going to square root all of that to get my total variance. Now, a shortcut to that would be 5 times 1.2 squared, so 5 days worth of variance, square root to get back to a standard deviation. So that answer would result in 2.6833. So 2.6833. So over the course of 5 days, I expect to groom 40 dogs. Very simple to understand. But I know that the number of dogs is going to deviate, like everything else in this world, and it's going to deviate by 2.6833 dogs. Hopefully you understand how I combine that. Okay, she makes $20 for each dog she grooms. In one day, how much money does she expect to make? Well, let's see. In one day, I expect to make, let's see here, 8 dogs times $20 per dog. 8 dogs times $20 per dog gives me a grand total of $160. That's very, very simple. Multiplication of a constant does affect the measures of center. How about the standard deviation? Well, once again, I expect a standard deviation of 1.2 dogs, and all I'm doing is converting that to a money, so I am allowed to multiply. Multiplication does affect standard deviation, so 1.2 times 20 would be $24. So I expect to make $160 a day, but that's going to vary by $24. Okay, in one 5-day work week, how much money does she expect to make? And with what standard deviation? Okay, so once again, we expect $160 per day. So the first day I expect $160, second day $160, third day $160, fourth day $160, fifth day $160. Now I know I can just do 160 times 5, and that is essentially what you're doing, but I just want to make sure that you understand that this is what's occurring over the course of 5 days. So that's $800. That's what I expect. Now, what about a standard deviation? Well, I know it's $24 per day, but I'm not allowed to add standard deviations together. I have to do 24 squared, variance for the first day, plus 24 squared, variance for the second day, 24 squared, variance for the third day, 24 squared, variance for the fourth day, 24 squared, variance for the fifth day, giant square root around all of that. And I know you could shortcut that by doing 5 times 24 squared inside the square root, and you would get $53.67. So follow along with me on your calculator just to make sure that's right, but $53.67. So over the course of a 5-day work week, I expect to make $800, but that's going to vary, and it's going to vary by $53.67. So this is an example of combining random variables and making sure that you understand how to combine them. This middle one here, this problem right here, is the idea of just transforming to money, which is very easy, just simple multiplication. Okay, now what I want to do is I want to take a look at a problem that is for a continuous random variable here, okay? And this problem hopefully will also make a lot of sense, but we are going to need the normal model for this one because it tells us the distribution is normal, which is huge. Okay, so Joey needs his tea to have between 8.5 and 9 grams of sugar for it to taste just right. So one morning, Joey adds 4 packets of sugar to his tea. Now, suppose that the amount of sugar in a packet follows a normal distribution with a mean of 2.17 grams and a standard deviation of 0.8 grams. What's the probability that Joey's tea will taste just right? Okay, so Joey needs between 8.5 and 9 grams of sugar for his tea to taste just right. So we know that this follows a normal model. By now, hopefully everybody knows what a normal model looks like, right? We know it's this beautiful bell shape. We're right smack dab in the middle. We have the mean, and then we go up 1, up 2, up 3, down 1, down 2, down 3, standard deviations, and so forth. But here we're not talking about 1 packet of sugar. Joey's putting 4 packets in. So each packet of sugar is itself a random variable. you're not quite sure exactly how much sugar is going to be in that packet. But we're putting 4 packets together. So we need to think about what do we expect to happen over the course of 4 packets of sugar. Well, we know that the first pack is going to have 2.17, as expected. The second pack, 2.17. The third pack, 2.17. And the fourth pack, 2.17. Once again, I know you can easily multiply, and I don't have a problem with that, but I just want you to understand the idea is that there are actually 4 things going on here. And if you multiply or add, you get a grand total of 8.68 grams of sugar. So if we got the average, we would certainly be happy because we would be between 8.5 and 9 grams of sugar for his coffee to taste just right. Sorry, tea, not coffee. However, the problem is this number is going to vary. And what's the standard deviation? Well, we know the standard deviation for 1 packet of sugar is 0.08, but we're talking about 4 packets. For the 15th time in this video, we're not allowed to add standard deviation. We have to add variance. So it's going to be 0.08 squared for the first day. Now I'm talking combine the other problem. For the first packet, 0.08 squared for the second packet, 0.08 squared for the third packet, and 0.08 squared for the fourth packet. And then I need a giant square root to change all of that variance back to a standard deviation. So this number is going to be 0.16 exactly grams. So now that we know what's going to happen for 4 packets of sugar, we can now start to answer our question. Now I'm going to draw a normal model here so that this looks nice and pretty. And that is a ugly line. So here's my normal model, right? Okay, not too bad considering. So I expect my normal model to have 8.68 grams of sugar for 4 packets. Now, I need to find 8.5, which is going to be a little bit below, somewhere down here. Here's where 8.5 is going to be. And 9 is going to be somewhere up here. And as long as I'm between 8.5 and 9 for my 4 packets of sugar, as long as I'm in this area, I'm pretty happy. So how do I find the probability that I'm in this blue area? Well, I need to find my z-scores for 8.5 and my z-score for 9. So let's do that real quick. So my z-score, 8.5 minus, I expected 8.68, that's the mean, divided by my standard deviation for 4 packets of 0.16, and I get a standard deviation, z-score of 8.5 minus 8.68 divided by 0.16, standard deviation of negative 1.125. Okay, so that's the position of this mark. And then my z-score for 9 would be 9 minus what I expect, the mean to be 8.68, divided by 0.16, and I get 9 minus 6.68, divided by 0.16, and I get, 9 minus 6, I typed something in wrong on my calculator. I get exactly 2. I get exactly 2. 9 minus 8.68 divided by 0.16 is exactly 2. So that means that this is at the exact mark of 2 standard deviations above. This is negative 1.25 standard deviations below. So now I could use my calculator, because if you remember on your calculator we have this famous normal CDF. Normal CDF, you put an interval in of a z-score to a z-score, and it'll give you the percentage of data in between that. So I'm going to go from my low, negative 1.125, to my high of 2. And when I do that on my normal model, negative 1.125, comma 2, I get a normal, I get my probability of 0.8470. So there's an 84.70% chance that I will have between 8.5 and 9 grams of sugar, and that means my tea or Joey's tea will taste just right. So the start of this problem was understanding how to combine 4 packets of sugar, and then the final part of this problem was basically something that we've already learned dealing with the normal model. All right, let's look at one more problem here. Okay, final kind of tester problem here. All right. What is the amount of time to prep a car to be waxed, follows a normal model, what they mean of 12.6 minutes, a standard deviation of 2.1 minutes. So to prep a car to be waxed takes around 12.6 minutes, but it does deviate by 2.1. The amount of time it takes to wax a car also follows a normal model. Sorry for the typo there. Let me throw the little L in there. With a mean of 15.8 minutes, a standard deviation of 1.3. So first question, what is the probability it takes over 30 minutes to prep and wax? To answer this question, I first need to consider what do I expect for prep and wax. So I need to combine some random variables here. So the total time is going to be prep, 12.6 minutes, plus wax, 15.8 minutes. So 12.6 plus 15.8 is a grand total of 28.4 minutes. 28.4 minutes. Okay, I'm going to bring another different color out here. All right, so now for the standard deviation for the total time, once again, I'm not allowed to add standard deviation. How many times have we heard that? You're going to hear a lot in class as well. But I can add the variance for prepping, 2.1 squared, plus the variance for waxing, 1.3 squared. And then I could square root all of that to get back to a standard deviation. And that gives me 2.4698 minutes. So, could it take over 30 minutes? Absolutely. Well, because I expect 28.4, so it should take under 30 minutes, but because things vary, it could take over. So if I think about a normal model here, I think about the fact that right smack dab in the middle here is 28.4. Somewhere over here is 30. And then anything above 30 is the answer to my question because I'm looking for over 30 minutes. So I need to find its position on the normal model. And z-scores tell me the position. So 30 minus 28.4 divided by the standard deviation, 2.4698. And let's see here, 30 minus 28.4 divided by 2.4698. Gives me 0.6478. So I have a z-score of 0.6478. So very, very close. Maybe I should have, 30 minutes is actually a little bit closer, very close to the means. In fact, it's less than 1. So now to find the probability of being over 30 minutes, I'm going to go to my normal model, my normal CDF on my calculator. I'm going to ask it to start at that position of 0.6478 and go all the way to 99, all the way to more. And that gives me, let's see here, 0.6478, 0.6478, comma 99, and I get 25.86. So 25.86% of the time, it will take over 30 minutes to prep and wax a car. So again, first part of the problem was combining random variables to understand the total. Second part of the problem was being able to convert it to a z-score and to think about the normal model and where that probability lies. Okay, last question. What is the probability it will take longer to prep a car than to wax a car? Well, if you think about it, it's supposed to take longer to wax. Wax is 15.8 minutes. Prepping is 12.6. So I first need to figure out what difference do I expect. So if I take 15.8 and I subtract 12.6, I get a difference of 3.2. I expect it to take 3.2 minutes longer to wax. But because everything deviates, imagine a situation where the prepping deviates a little bit high, the waxing deviates a little bit low, and all of a sudden it actually takes longer to prep. It could happen. So what about the standard deviation for the difference? And this is really, really important. I'm going to put a big star here. Pay attention. Standard deviation never adds, nor does it never subtract. Variance always adds, and variance always adds. Okay, what do I mean by saying that twice? I mean that variance always adds. Even when you're combining two random variables and looking at their difference, you don't lose variance. Variance always builds up. So it's still going to be 2.1 squared variance for the prepping plus 1.3 squared variance for the waxing. It doesn't change. Just because I subtract, I'm looking at the difference, doesn't mean that I subtract variance. Again, anytime you put two random variables together, whether you're looking at adding them together or subtracting them to look at the difference, the variance between them is always building up because you're still putting them together. So it's always building up no matter what. So that's important to understand. So now if I take a look at a normal model here, I understand that right smack dab here is the 3.2 minutes that it's supposed to take longer to wax. Now, the most important number that you need to find here is 0. Because 0, somewhere down here, is where we have a tie. Prepping and waxing takes the same. There is no difference. This side of 0, waxing takes longer like it's supposed to. This side of 0, prepping takes longer like it's not supposed to. And I'm trying to find anything below 0 because if you subtract wax minus prep and you get a negative number, then it would take longer to prep. So that's what I need to find, is that area down there. So the key number here is 0. I need to find the z-score for 0. So I'm going to subtract 3.2. I'm going to divide by 2.4698. And let's see here. That is negative 3.2 divided by 2.4698. That is a z-score of negative 1.2957. And I need to use my normal CDF. And I need to look from negative 99 all the way to that z-score. And that will give me the percentage I want. So let's see here. Negative 99, comma, that value is going to be 9.75%. So 9.75% of the time, I will be in this area down here with a negative difference below 0. So, quick recap. Transforming, you're just converting. You're just taking a single random variable and you're maybe changing it to money or adding a constant. We understand how that affects. Then we have combining random variables, where we're putting 2 or more random variables together. Be careful. You're allowed to add means. You're allowed to subtract means. But when it comes to standard deviation, A, it always builds up, and B, you never add standard deviation. You always have to add the variance first. So if you need to, go back and review these problems, especially if you need help on your quizzes or anything like that. But hopefully these helped you better understand how to combine and how to transform random variables, and you understand the rules.